Welcome, everyone. It's my great pleasure to introduce you François Lazeras, who is the head of the CIBM MRI UNIGE clinical MR imaging section, who will be chairing this session today, which the speaker is Patrik Vuilleumier, who is also the new head of the new section, MRI UNIGE. So I will stop sharing my screen, and François, you're welcome to introduce.
Yes, good morning, everybody. So today I have the pleasure to introduce Patrik Vuilleumier, well known in Geneva. He's a full professor in both the Department of Basic Neuroscience of the Medical School of the University of Geneva, and also involved in the clinical department of neurology at the University Hospital here in Geneva. So Patrik is a kind of in-house personality. He grew up in Geneva. He has got his medical degree at the University of Geneva, and he moved for his medical degree or equivalent of PhD in at the CHUV in Lausanne. So he knows all the Lémanic region pretty well, and he finished his FMH. A specialty in neurology here in Geneva. And after he moved abroad, 2 years in the States and 3 years in London at the UCL, in the well-known Wellcome Center for Neuroimaging, which was led by Frakowiak at this time. And after he moved back in Lausanne, in Geneva, sorry, as an assistant professor. He was an FNS professorship at this time. And 2002 was the time where I start to know him pretty closely, because he came to the radiology to do his research on fMRI. And this time it was pretty tough. We had to struggle with a single 1.5 Tesla machine, which was shared by the heavy clinical work and research from different groups. And Patrik was one of these most active group at this time. So until 2006, and 2006 for Geneva was a time where the 3 Tesla CIBM system was installed. So you see, we had a good 4 years of struggling, working during the evening and the night for doing neuroscience and fMRI studies. So just to close the parenthesis, in 2007, he became full professor in neuroscience in Geneva. And in 2009, he founded the BBL, Brain and Behavior Laboratory, that is now linked or part of the CIBM as well. So it's a very good story where you see that other initiative and our system are linked and work together. So I really look forward to work more closely. And finally, in 2016, he became co-director of the Campus Biotech imaging platform, which is shared with Olaf Blanke. Okay, that is for his itinerary. Patrik has an extremely impressive track record. So he has more than 260 publications. I certainly forgot some of them. I just went through the different platform, like, okay. And with H-index of 78. So he participated in 20 Swiss National Fund grants as PI or co-PI. And right now is on 3 running grants, a Synergia, R-Equipe, which was just accepted last year. And thanks to this R-Equipe, he could last month update his Trio to a Prisma Fit system, the same that we have in at the Hug in Geneva. And he has also ongoing ground on neurofeedback and modulation. And also as a parenthesis, this grant is also in connection with the work of Dimitri and his team. So you see that we have a good relationship between the CIBM and the different entities. So his main interest is attention, especially for clinical work and neglect symptoms, awareness, emotional, and social cognition. So it's very interesting because it will be the first application of MRI toward cognitive science for the CIBM. So we really look forward to have a close relationship with Patrik. So with that, I will finish and I will stop sharing and I will let Patrik make his presentation.
So yeah, indeed, it's a great pleasure to talk today and to join this group of experts in imaging in the limbic area. As Francois said, we've been very close for many, many years and collaborating on many different projects. And in fact, for the talk of today, I've chosen to present one line of the research of our group that indeed spans almost 10 different years. I realize that it's more than 12 years since we are working on this topic, which shows how stubborn I can be and how slow research goes. And also it illustrates the productive and very nice collaborations we had with different groups from CIBM, Dimitri Van de Wiel in particular, but also Christophe Michel for many, many years. Okay. So as Francois said, one of the field of research of our group is emotion. And there are many different ways to consider and to study emotion. I won't go into many details and debates and questions about what are emotions, how do you define them as compared to other mental events. But one aspect, I'm sorry, it doesn't seem to move. Okay. One property of emotion is that it reflects a change of the brain, a change in the organisms, supposedly with the goal to adapt or to respond to some situation that have a particular meaning. And what is important is that emotions cannot be defined really by a single phenomenon. There's not one particular characteristics that will characterize a brain state or mental state as being emotional. But emotions are, I think, in essence, a multi-component process. There are, of course, changes in cognitive states, in attention, in action tendencies, in motivation, what you want, what you don't want, motor aspects. And all this combination, this cocktail of processes make up an emotion. So it's not a single process. And in line with this, in fact, now 2 decades of research on brain correlates of emotions have clearly shown that this is involving much more than one single brain region, but typically an activity of many interactive regions. And even if some regions seem to be particularly important in emotional processes, for example, the amygdala, which is very well known in fear, but also other emotions. One of the reasons probably it's also important is that it's very much connected. In fact, the amygdala aficionados will say that this is the most connected brain region, which has relationships, bidirectional relationships with virtually every other brain region, such that in fact it can influence very rapidly, effectively, the activity of many other brain networks. And one aspect that I've been particularly interested in is that emotions are intrinsically dynamic. I think they are precisely a change, a response to a given situation. And because of that, in some sense, there is by necessity a state before and a state after emotion, in the sense that what the emotion will trigger is a change, and we can assume that the state of the brain will be different once the emotion has emerged. And there is a dynamic process with not only effects related to the event itself, to the episode of an emotion, but also effects that may persist after an emotion. And in fact, in psychology, there are a number of observations and a number of research showing that emotional events can produce lasting effects on perception, on memory, on preferences, decision-making, and mood, for example. And clearly, if you received the bad news this morning, probably your state of mind, your actions, your desires will be different for at least the rest of the day, as opposed if you had, bad news. And so these changes triggered by emotions can have lasting effect. And in some sense, it struck me that this is in contrast with a lot of the research that has been done, that I have done in the past when studying emotions, where people typically have been using very isolated stimuli presented one by one, and for experimental good reason, many times in pseudo-randomized, unnatural sequences, like showing one face with fear expression, then fear with disgust or with anger, mixing with voices, music. With, in some sense, the assumption that you create an emotional response or an emotional brain activity on the background of neutral activity, and that once this activity is evoked, this emotion is evoked, you return to a sort of neutral state that would be similar to before. And clearly, this is not how emotions arise in real life. And so this frustration I had, in some sense, in the research, came at the same time as another frustration or another interest in brain imaging, which you all know very well within CIBM, in particular with the work of Dimitri and Christophe, is that since a number of years now, it's clear that the brain activity is made of ongoing activity within organized networks that have ongoing intrinsic activity, even during rest, even during various tasks, such that different brain areas tend to interact preferentially with some other brain areas. Typically, for example, the motor cortex. Motor areas will tend to, motor cortex will interact mainly with other brain regions involved in motor function. Visual areas will tend to interact, have ongoing connections with other visual areas, and so on. And in some sense, mental events, cognitive functions are brief and transient changes in the configuration of this ongoing activity that will support particular computation. And these changes in brain states will build up and appear and vanish on top of ongoing activity. And among these ongoing activity in the brain, there is one particular network that has attracted a lot of attention, which has become known as the default mode network. But as you will see, it's clearly not a mode by default. Although the nature of the exact function of this network is still not very clear, and if there's only one, it's not very clear if there's only one function. But one of the striking aspects is that it's really overlapping with brain regions that are involved in affective processes and emotions, particularly in emotional regulation, self-awareness, interoceptive awareness, self-memory, but particularly affectively loaded self-memory. And the second frustration in the research I had when this research came was that initially default mode network was considered as a sort of static network that would have its existence on its own, and resting state to me looked like, I had friends at that time who were doing cognitive experiment that were arguing that resting experiments are for lazy scientists because you observe ongoing brain activity without having to bother to create an experiment. In fact, I wanted to show, and I hope what I will show you, that in fact resting activity can be considered as an experimental condition and can be manipulated. And specifically, one of the questions we have been asking is how this configuration, this ongoing activity, intrinsic activity in the brain will be changed by emotions, and what is the dynamic of these changes. Are some of these changing occurring not only during emotions, but also after an emotions, and do they account for changes in behavior that are associated with emotions? And in particular, what is the role or the impact of these processes on the so-called default mode network, which is a prominent configuration of activity at rest, at least when you ask people not to do a specific task. So many years ago, we started to ask this question with Andy Vuilleumier, who is now professor at Harvard University, who was an engineer, and I had a hard time to hire a PhD student in neuroscience who was an engineer, in fact. And we decided to do a very simple experiment. And in fact, this paradigm has become the motif or the protocol that we have been revisiting in many different ways since more than 10 years. As you will see, it's extremely simple. And many of what I'm going to present is derived from this very simple experiment. So in this experiment, we typically present movies that last between 40 and 60 seconds. And these movies were selected for their particular emotional content, so they could evoke different emotions. And in particular, in that experiment, we took movies, both famous or less famous movies that would evoke fear or anxiety, and movies that would be quite fun or elicit more joyful states. And critically, in this experiment, after the movie, we present period of rest, where we ask participants to do what typically is asked when you do resting state study in neuroimaging. So you ask people, please keep your eyes open, fixate the cross, and let your mind wander without thinking about anything in particular, which is a sort of very broad instruction, but that's how it's typically done. And in our experiments, we just explain to the subject that's the way we typically do experiments, on emotions. We show movies that elicit emotions. That's what we are interested in, and then you have to rest because the brain has to recover, and that's we need a control comparison. That's how we do experiments. But in fact, in that particular studies, we were interested in the rest period and not that much in the movie. And we were interested to know how seeing movies with different emotion scenes would influence how the brain would rest subsequently. We also asked every now and then, but I won't be discussing too much, and it depends on some of the paradigm, but some questions, surprise questions about, in fact, what people were thinking actually during the movie. And the main result we get from this type of studies is that indeed, after seeing or experiencing emotions, the brain does not return to the typical resting state. And for example, if you do a very simple classic contrast statistics between brain activity at rest after an emotion compared to brain activity at rest following a so-called neutral state, we see that there are changes in brain areas that really correspond to the default mode network. So medial prefrontal regions, medial parietal regions, and some other brain regions. So in fact, following an emotion, the brain is not really returning to the normal rest. And this is seen both following exposure to negative, fearful content or positive, joyful content, with some differences, but overall it's quite similar patterns. And interestingly, there is also a dynamic or time course to these changes. If you slice the brain activity during rest in different time windows, different periods, in that case, because we had 90 seconds resting cycles, we split the resting blocks into 30-second time windows. You can see that there are some areas, like one area within the default mode network, the posterior cingulate cortex, that show a typical resting state pattern, in the sense that when people watch the movie, this region is deactivated or looks like relatively deactivated, disengaged. And for very exciting, absorbing movie, fearful, joyful, it is more disengaged than for less interesting neutral movies that were documentaries about Swiss trains and building of tunnels and so on. And after the end of the movie, the brain, or this brain region, returns to its resting baseline, and as soon as the movie is finished, goes back to this baseline activity. But some other regions within the brain, the default mode network, show a different pattern. They are also disengaged during the movie, but when the movie ends, they do not immediately return to normal state, and they go back to their resting level progressively following the fearful or the joyful movies, whereas if the movie was neutral, the region goes back immediately, in some sense, to the resting level. And this pattern was found also in other brain regions that were in that experiment modulated by experiment and active at rest as well, where you see that there is a progressive return to resting baseline, but only in the post-emotional condition and not following a neutral, more boring movie. And that's also the time where we started collaborating with Dimitri. And of course, at that time, Dimitri was very much interested in wavelet analysis, and we performed a number of studies trying to assess brain connectivity and changes in brain connectivity. So how different regions co-vary in time together with these data to assess indeed how emotions would change the conversation, the interactions between brain regions following emotion. So we applied some of the methods that Dimitri had developed to look at these changes. And indeed, we saw that emotions would change in a lasting way, at least during the several minutes of rest following emotional movies. The connectivity between specific brain regions, not all brain regions, but really specific connections. And in particular, we saw again that connections between the amygdala, which is very important regions in emotion processing, would be selectively decreased, show a selective decrease in connectivity with medial prefrontal cortex regions, both after fear and after joy. Whereas it would show an increased connectivity with cingulate cortex, for example, more specific to fear. And interestingly, we found that in these post-emotion resting states, one new hub area would appear in the resting state networks, and which is the insula, which became very connected to other regions typically associated with the default mode network, such as the precuneus, posterior cingulate cortex, inferior parietal cortex. And this area is very well known in interoception and feeding states, as if now default mode incorporated more of signals and information, recruiting the insula and involved in monitoring bodily states. And this was found both after fearful movies or joyful movies, with some differences in the frequency band that was most affected, with changes affecting faster connection, faster fluctuations post-fear and slower fluctuations post-joy. But that's something we can speculate that after fear, maybe the brain is in more unstable states, but that's a speculation. And very interestingly, the changes in these connections we found was very strongly correlated with personality score. For those of you who may be old enough or have followed literature on brain imaging and individual differences, this is typically what some people would qualify as a voodoo correlation. You say that it's extremely high. But it's also extremely selective in the sense that it's really affecting these only connections that have been affected by the previous emotional movies. And as you can see, these are anxiety questionnaires, so state, trait, anxiety inventory. The higher people score on anxiety questionnaires, which are within the normal range, they are not clinical anxiety, but the more people tend to be anxious, the stronger these connections will be impacted by the previous movie, which shows that indeed the way the brain recovers from emotions and return to its resting, so-called resting state, will be influenced by how anxious or how efficient the emotional regulation mechanisms of the participant are. And interestingly, in this experiment, like in many others we have seen, this correlation with personality score found only during the resting state and are not significant, for example, if we test the same correlations during movie watching. And they are not significant, for example, in that particular experiment, if we use other personality measure, for example, related to depression or to mood, whereas in similar experiment where we manipulate pleasure or rewards, we see that changes in specific connections will correlate with anhedonia and depression questionnaires, but not with anxiety questionnaires. So it looks like not only connections, but specific personality traits are specifically affected by these manipulations. So to summarize this first series of studies, I think what we have found or showed with this experiment is that in terms of emotions are not isolated episodes that are followed by just a return to the exact previous state of the brain, but they have an inertia, as it is often discussed in psychopathology or in clinical psychology. There are lasting changes in brain activity following emotions, which can be observed at rest, which people are not supposed to do any task. There are common effects of positive and negative emotions that affect the so-called DMN network, in particular ventromedial prefrontal cortex, and there are new insula-centered hubs in resting state networks. As I said, the insula being implicated in self-bodily monitoring. And we also found distinct effects more related to the valence, with fear specifically affecting connectivity between anterior cingulate cortex, which is involved in alerting, salience monitoring. And these connections seem to be quite specifically sensitive to individual anxiety traits. And we think that these changes reflect the intrinsic dynamic properties of emotional regulation systems that, in fact, allow the brain to recover from emotional stimuli. And I won't go into details, but we've replicated these effects with, as I said, reward task, stress task, odors with different movies, and so on. So more recently, we've continued in this line of research with variants of this paradigm. And one recent variant of the paradigm I would like to present is one that was part of the PhD of Julian Gaviria, where we basically used exactly the same paradigm, but now using longer movies and longer resting periods. So people watch long scenes of 5-6 minutes of movies, followed by resting periods of 8-10 minutes. We wanted to see how long these changes would persist for, and we wanted also to see how they interact with changes that can be produced by purely cognitive processing. So the task was, the movies were followed also by a performance of different cognitive tasks. And here again, we collaborated in part with Dimitri's group, and to analyze the changes in the dynamic of the brain between movies and resting periods, we applied this co-activation pattern analysis that has been developed and used partly by Dimitri's group. So I won't go into details because I assume that most of you know these techniques, were, which is based on looking at the occurrences of particular configurations of connectivity with particular regions and look at their changes and presence over time. And so when we apply this method to this paradigm, so where we had either neutral movies, sad movies, resting period following the movies, or resting period following task and movies, we found that there were 8 different co-activation patterns, 8 networks that were fluctuating over time and showed changes in their connectivity with a key node of the default mode network, the precuneus. And interestingly, only 3 of these different networks were significantly modulated by the emotions of the preceding movie. And again, one of these networks was overlapping with the DMN network. And another network was overlapping with the attention network, the dorsal attention network, and which both were tended to be increased following emotion, the sad movies, whereas one network overlapped with motor and sensory areas and tended to be reduced following emotional movies. And when we look at the temporal parameters of this co-activation pattern analysis, we do see indeed that this DMN network is selectively more present following exposure to the sad movies as compared to exposure to neutral movies or to other conditions. And in parallel, this other network that corresponds to the dorsal attention networks is selectively increased following emotional movies and performance of a difficult attention demanding task, so a Stroop task. So it's sensitive to an interaction between emotion and the cognitive effort of the task. And Julian also examined whether these changes were correlated with the performance or the different behavioral measures, and observed that the increase in the presence of the DMN, or the changes in the DMN activity following the emotional movies, was very significantly correlated with changes in subjective affect of the participants. So the more the participants reported to be in a negative affect following the task and following the movies, the more the DMN was impacted in the resting state following the sad movies. And conversely, the more the the attentional network was affected by the emotional movies, the more subject had difficulties in the cognitive tasks, which here is illustrated by an increase or correlation between this change in the attention network and reaction time in the Stroop task, and interference or distraction measure in the Stroop task. So the more, and this was selective for the negative context and didn't happen in the neutral context. So the more subjects were had difficulties following in the cognitive performance following a negative emotional experience, the more the DAN was recruited and the more difficult the performance was for the subject. And in this paradigm, we also had the opportunity to directly look at how these changes in the post-emotional resting state were in fact correlated or related to what happened during the movie itself. And we looked at how much the recruitment of particular networks during the movie will explain, in fact, the subsequent changes that you see in the resting state following the movie. And some of this work is still ongoing, but Julian already showed a number of interesting results. In this study, so we look at connectivity pattern with both the precuneus, that is a keynote of the resting state network, and the insula, which is this other network that becomes a hub during resting state movie, and that was very strongly activated also by emotional movies. And here we found 14 distinct configurations that were modulated over time, and 4 of these were sensitive to the emotional conditions. And again, they included the default mode network, but also one network, including frontoparietal cortex, overlapping with both the attentional network and the salience network, frontal areas that correspond to the cognitive executive control network, and some visual areas. And when we look at the changes over time of these networks, how their activity during the movie predicts their activity in the subsequent rest, we see that a very selective pattern where the more the frontoparietal cognitive network, so mixing salience and attention network, is recruited during the movie, in a neutral movie, the more the central executive, the cognitive executive control frontal areas is activated at rest subsequently, and the less the DMN. And this pattern is totally reversed after an emotion conditions, such that the more this attention and saliency network is recruited during the movie, the least the cognitive executive network is activated during rest, and the more the DMN is activated. So it's the more the brain will be engaged specifically by emotional content, the stronger the impact in this network, and the brain will be shifted in a different state with more presence of the DMN and less presence of more cognitive control areas. And also the more presence of the DMN during movie itself will also lead to reduced expression of the cognitive executive control network following the movie. So again, this more recent set of studies again shows that negative emotional events can produce a carryover, a lasting inertia on brain activity and brain network in subsequent rest. Again, the impact seems to be quite selective on this default mode network and systems that are involved in how the brain control itself. Cognitive control system, attention system. And we showed that they have a direct link with subjective affective ratings and behavioral performance in cognitive tasks. We think that these effects are reflecting how much the brain is indeed recruited by the movie itself, how much salience the movies can be, even when they have low arousal, where they are not exciting, but only have a negative valence with sad movies. And this is very consistent with a line of research in clinical psychology on a notion which is called inertia, which is reflecting how much emotional states tend to stick and persist over time, which has been associated with poor emotional regulation and a number of and higher risk for psychopathology, in particular depressive ruminations and risk for stress-related depression. And we, in fact, in more recent studies, we have shown directly that, in fact, if we ask then people to report about but following the scanning runs, if we ask people to report what they have been thinking of, we can show that indeed in some situations people tend to report more frequently ruminative content. And I think more importantly also what this shows is that resting state and this network indeed are not static. They are highly malleable and you can manipulate their expression in an experimental way. And I think this has implications for how you design resting state fMRI experiment, because in many cases, for example, in clinical studies, people will present one resting state run, scan acquisition following a cognitive task or following other emotional task. But in fact, what the subject has done just before, or maybe whether the experimenter was nice, pleasant, or maybe not that pleasant, will in fact influence the state of the brain, of course, and the resting state. And interestingly, if we assume that these changes at rest reflect a change in the configuration of the brain induced by emotion, and this has a sort of this fits with the general idea that emotions adapt the brain to respond to particular challenges. Oh, sorry, I forgot that's important. So we replicated also this more recently with collaboration with Christophe using EEG. So we did exactly the same classic experiment with movies, resting period, and so on. But now we recorded resting state EEG, and as you know, Christophe has and others have shown that you can also measure the presence of specific brain topographies during rest with EEG, and they've shown that some of these topographies do correspond to classic resting state network measured with fMRI, and in particular, this class C seems to be correlated with the expression of both the saliency and the DMN network, and class D seems to be correlated with, it's not very visible, but with some attention-related areas. And when we repeat our experiments with now EEG, what we find is in fact very consistent with the fMRI data, which is that this class C topography is selectively reduced following fear movies, whereas the attention configuration is selectively increased after the fearful movies with the EEG. So again, only these two networks seems to be sensitive to the emotional experience. Now, as I said, if these changes reflect some adaptation of the brain to respond to challenges, we can assume that this may have consequences on how the brain will react to subsequent stimuli. And that's something we've tested already quite some years ago with Swan Pichon when he was in my group. Again, same paradigm with alternance of movies, positive, negative, neutral. But now instead of resting, we ask people to do an attention task where they had to very simply, they were shown always 4 pictures, and they had to report whether 2 faces on the screen were the same or different. And on other occasions, they were asked to say whether 2 houses were the same or different. And that's a task we have been using for many years in other experiments to show that, or to dissociate the effect of attention on perception and the effect of emotions, because the faces can be fearful in that case or neutral. And in that case, we wanted to see how being exposed to particular emotional situations will change how people do this task. And of course, we looked at the effect in the amygdala, which is highly responsive to fearful faces. And following a neutral movie, we found what we had already reported more than 10 years ago, which is that it looks small because of the deviation, but in fact, there was a very significant response of the amygdala to the fearful expression in the faces, both when people were judging the faces and when people were judging the houses. Interestingly, when participants do this task following a negative movie, this response to fearful faces is amplified. And it's again, both when participants look at the faces or when they look at the houses. And in fact, even more interestingly, if they perform this task following the joyful, fun movies, there is a suppression of the amygdala response. Now, there is no difference between fearful faces and neutral faces, which again implies that to some extent how you do experiments, if subjects come in a good mood or bad mood, or if you tell them jokes or not before doing the experiment, maybe you can in fact change how the amygdala will respond. And this effect was not related to any change in the effect of attention itself or in the response of face sensitive regions like the fusiform cortex. And again, this effect was highly sensitive to personal anxiety trait, such that the more anxious a person would be, the stronger the effect of positive emotions, and the more anxious they would be, the higher the amplifications by negative movies. So that people with more anxious traits seems to be more malleable, more their brain or the amygdala responses seems to be more able to be shifted either positively or negatively following these events. Maybe I will skip this. So again, to show that what happened during the movie will predict what happened afterwards. And I think one of the last experiments I want to show is by Emily Kiao, who just defended her PhD recently. And she built on this paradigm now to look at how the same sort of manipulation would change perception of pain. And again, she presented blocks of negative movies, positive movies, or neutral movies. And now, after the movies, she gave to participants some thermal, painful stimulation, and she measured not only how people rated them, but also how their brain responded. And as you know, there are selective affective responses to pain that involve the insula and the cingulate cortex. And we found, again, that brain response in that case now in the insula to pain will be increased after a negative experience, whereas it will be reduced after a positive experience, after a positive movie. With a significant interaction and selective interaction across the whole brain in the posterior insula, with suppression of the difference response to painful and painless stimulation following the positive experience. So these changes induced in brain state following emotional events can not only change rest, but the changes in brain configuration will have an impact on how the brain will then react to new events, with changes at least in the amygdala, in the insula for fearful faces, self-perceived pain. And this is consistent with behavioral studies that have shown affective priming effect, so an effect of presenting emotional stimuli on some behavior. And I will not go into details, but we have also replicated this sort of effects in other tasks, including when you judge pain, not only in yourself, but in other people, or if you judge emotions expressed by other people, memory recall, cognitive attention control, or even decision-making. And the last thing I wanted to mention is the fact that this framework helps also to characterize or to understand changes that can be observed in clinical situations. And this is, for example, illustrated by the work done by two former collaborators of my group, Camille Piguet and Gladys Ray, where we also collaborated with Dimitri here. This is a study where we followed over, I think, more than 1 year, several years, patients with bipolar disorders who have periods of depression, periods of mania, and periods where they have normal mood, euthymic. And we scanned them repeatedly over time, whatever was the current mood states. And we looked at how their brain activity at rest would change according to their mood state. And what we found indeed was that, although these were the same patients, just tested at different moments, when they came on days where they were depressed, one network again was selectively more present, and this was again the default mode network that distinguished between depressive states and other states in the same patients over time, whereas other networks were not significantly modulated. And Camille is exploiting this paradigm also in other situations where we are looking at the effect of social stress, so where subjects have to perform a difficult or more or less difficult arithmetic task in a given period of time. So they are shown a bar that moves, and they have to solve this equation within the time. And after they gave a response, we give them a feedback, a social feedback, to stress them, that gives their rank, so how well or how bad they are doing. So we tell them, well, you're the best, or the second best, or you're almost the worst participant in terms of your response time. Please do better. And again, here what we look at, what is most interesting, is not necessarily how they perform the mathematics, but how their brain will then rest if we have a period of rest after difficult, after trials where they get consistent negative feedback, which is manipulated. And again, we see that there are changes in the feedback period following the feedback in ventromedial prefrontal cortex, so a keynote of the default mode network, which seems to be enhanced and more extensive in euthymic, in patients with depression, even though they have a normal mood at the time of the experiment. And interestingly, during this feedback period, the patients also show an increased or reduced activity in the striatum, so one region that is typically associated with reward. Although this is again during rest. So to conclude, I think in general, these studies on resting state and their manipulation by affective states converge with another line of research that we have, and a view of emotions as being dynamic changes in a system, where you can conceive emotions as, you would perturb a system, like throwing a stone in the water. Big stone will produce big waves, and small stones will produce small waves, but the waves do not disappear immediately after the stone has been thrown in the water. So that the quality of the liquid and the strength of the stone will determine the change in the system. And any new system, and if there is a body or a new event riding on these waves, the path and the trajectory of this new process will be determined by the state of the system. And not only one can consider that emotions will be transitions from one configuration to a new configuration to adapt the brain to a particular situations, but there is also a path that is constrained on how the brain returns to a normal state. And this may be influenced by the history of the system, by the properties and the plasticity within the system, which correspond, for example, to personality traits or to previous history of the subject, and one can conceive attractor states that would be typical or atypical or pathological in some clinical conditions, and be associated with emotion dysregulation. So overall, I hope I've shown you that emotions can be considered as indeed involving changes in extended and distributed brain networks. And interestingly, have also to be considered in time, not only in how they change the spatial configuration of brain activity, but how they evolve over time. And I think this goes beyond the more traditional approach to emotion, which is to focus on very transient responses in isolated regions, like typically the amygdala, which is one of the top brain regions within emotion processing. And our findings converge with this psychological notion that emotions can have an inertia that is associated with different emotion regulation capacities, and in turn will affect how the brain reacts and behaves in new subsequent situations. As I said, this can change cognitive performance, affective performance, and be a reflect of individual capacity in emotion regulation, including abnormal emotion regulation or just cognitive biases that are observed following emotional experiences. And I believe that these measures of changes following emotional events can provide an interesting biomarker or an interesting index of the capacity of the brain to adapt to emotional challenges, and a measure of maladaptive responses in some situations, or at least risk, for example, for pathological conditions. Well, and all this work is, of course, done by a number of very active, clever, and productive people in my group who have spent quite a few years working on these issues, but also, as I mentioned, a number of colleagues, including in the CIBM, with whom I hope to continue this adventure in the following years. Voila, if you have any questions.
Okay, thank you very much, Patrik. Thank you for this small journey in the brain and in our mind. I hope that we didn't lose too many people during this trip. I don't know if there is any question in the audience. Please raise your hand or just ask your question.
Patrik, an obvious question from my side. How long you think this effect, this influence on the resting states could be?
Well, it's like the famous joke, a certain time. As I said, with the longest we've looked at the recent studies of Julian, where we looked at typical resting state studies showing, you have 6 minutes of movies and then 10 minutes of resting state. So even 10 minutes after, it looks like there are still some traces of what happened before. I would assume it depends on exactly what is the event and what is the measure. I mean, interestingly, it's known that even in animal models, for example, of depression, some changes, for example, in relation to stress and cortisol can be very lasting and have a predictive role. For example, if you expose animals to stress, social defeat, typically, for example, of course, they have very high cortisol right after, but 24 hours later, some of them still have high cortisol, and these are the ones that tend to develop more, depressive-like symptoms. Yeah.
Because, I thought that you said it can be a biomarker for maladaptation in certain diseases, but it could also be a therapy, if it lasts long for certain emotional diseases, like PTSD or subjects like that. If you would expose them to these videos repeatedly and it has long-lasting effects. Maybe that could be a therapeutical approach, no?
Yeah, I hope. Yeah, you can certainly, the brain can learn, I guess, also for good, for good.
Right, exactly.
So yeah, sure. I mean, the fact that hopefully some therapy work precisely shows that, you know, you can induce by talking to people changes that have a lasting effect on their brain and their mood. So yeah, sure, yeah. And indeed, I mean, as you know, we have also some interest in neurofeedback. I guess one impact, for example, of being exposed, for example, in, you know, we could imagine like virtual reality or some just game type of feedback will induce some new configuration, or at least increase the probability that this configuration is visited, and then that could be beneficial as well.
Mm-hmm.
Okay, is there an other question in the Zoom audience? I have just one, I mean two. One which is more like fundamental question, which is the left versus right brain.
Voilà.
And yes, I'm all the time very surprised to see that there is never a kind of left-right asymmetry. So in the emotion and what you have done with the amygdala, do you point out a kind of asymmetry, or the role of the left versus right hemispheres?
Yeah. Right-left brain are clearly different, and they are, you know, if you do a language study or face study, you will see, you know, changes more on one side or the other. And even resting states, as you know, there are some networks that are more lateralized, and I mean, you find sometimes left lateralized, right lateralized. Now, within emotion, it's true that there is a discrepancy between some traditional view from neurology that the right hemisphere should be the emotional affective brain, although this has always been debated, whether this is at the level of perception, expression, recognition. That's always been debated. But imaging in general has shown relatively little lateralization in so-called emotional system. And the amygdala in particular, there have been many studies, meta-analysis, trying to figure out, you know, when the right is more active, on the left is more active. And I think there is no real consensus of people have come up with the idea that women have more one or the other, that block design, event-related design, negative, positive, conscious, unconscious. Many people have their sort of little theory, but consistently, I don't think the amygdala in particular, or some prefrontal cortex regions themselves will be lateralized in relation to emotion. However, depending on which hemisphere an amygdala lives, it will see the world probably differently, right? Because it will receive information from right visual cortex or from left visual cortex or from more voice or language related content or more, you know, face social content. And so in some sense, it's more the domain and the material on which the one part of the system will respond to than what it is doing, I think.
Okay. Thank you. Other question? Okay, so I thank you again. I think there is no further question. I think we can stop here.